In this presentation, we're going to discuss processes. Now, processes are essentially the runtime equivalent, or is a program in progress. It is a program running. And here we're going to talk about the concept of a process, scheduling, operations, interprocess communication, and various examples. An operating system executes a variety of programs. Now, originally we had batch systems which executed jobs, which are kind of similar to process. And then we had time-shared systems which used user programs or tasks. Job and process are used almost interchangeably, although these days you rarely hear the term job. Process is a program in execution. Process execution must progress in a sequential fashion. So here are some concepts. The program also called the text section, is the actual machine code for the program. A current activity includes a program counter as well as a processor register set. There's a stack containing temporary data, for example, function parameters, return addresses, and local variables. There's a data section containing global data, and a heap containing memory that's dynamically allocated during runtime. Think of new in C++ or other languages. A program, however, is a passive entity stored on disk. It's just a file. Process is active. A program is transformed into a process when the executable file is loaded into memory, and then it is no longer just a program. Execution of a program is started via mouse click, command line, a number of other ways too. A single program can contain several processes. For example, multiple users executing the same program, each would have its own process. If you look at the task manager in Windows and you're using Chrome, you'll see many processes, for example, that are all Chrome. So here's a drawing of the process in memory. We've got our stack, which grows down, our heap, which grows up, our data section, which is limited, and our text section, which is our actual code. So here would be an example in C++ of how this would break down into a process. And we have our stack, and here when we have our method, when it's called, we're going to push our parameters onto the stack. Here, when we do a malloc, we're going to push that onto the heap. We're going to have our uninitialized data, X. We have our initialized data, and then we have our text, which is the whole of the program. Notice it goes from high memory to low memory. Each process is in a state. As it runs, it progresses through various states. There's a new state, it's being created. Running, instructions are being executed. Waiting, the process is waiting for some event to occur. Okay, so you're kind of stuck there. Ready is when the processor is waiting to be assigned to a processor. And terminated means the process has finished execution. So here's basically a map of the various states. For new, we get admitted to ready. From ready, we can move to running. From running, we can move to exit. We can move back to ready if we're interrupted. From running, we can also move to waiting, where we're waiting on an event. And from ready, we can dispatch into running. Finally, we can go to terminated. Every process has a process control block. It can also be called a task control block or a process control context. I like PCB the best. In it, we have a process state. It's the state of our current process. A process state, which is running, waiting, etc. A program counter, the location of the instruction to next execute. Because remember, if we have multiple processes and they switch, they won't be executing at the same place. We also have CPU registers, the contents of all process-centric registers. We have scheduling information, such as priorities, scheduling queue pointers, etc. Memory management information, memory allocated to the process. We need to know what's been allocated. Accounting information, which CPU is used, clock time elapsed and start, time limits on a process before it has to switch, and I/O status information, I/O devices allocated to the process, and a list of open files. There may be more information, but this is an overview. So when a process runs, we begin executing. There's an interrupt or a system call. We state to get us to switch processes. We save the state into the PCB. When we're switching processes, reload the state from PCB at process 1. If there is an interrupt or system call happens, we then save the state of process 1 into a PCB, and we reload process 0 and continue executing. And this goes on and on no matter how many processes you have. So far, processes have had a single thread of execution, considering having multiple counters per process. Multiple locations can execute at once. These multiple threads of control are called threads. They must have storage for thread details, multiple program counters stored in the PCB. In the next presentation, we'll talk more about it. So in Linux, how are processes represented? It uses a task struct in C, where we have a process ID, the state of the process, the time slice for scheduling information, the parent process, its children, the open files, and the address space of this structure, or of this process. We've got the task struct information and is used by the various processes and updated for each as we switch processes. Now, process scheduling is very important. It maximizes CPU use, quickly switches processes onto the CPU, and essentially imitates time or affects time sharing. So, the processor schedule selects among available processes for the one next to execute. It maintains scheduling queues, and it'll have some of the following: a job queue or process queue, which is all processes in the system; a ready queue, set of all processes residing in main memory, ready and waiting to execute; device queues, set of processes waiting for an I/O device, and the processes will migrate among the various queues. So here, as an example, in our ready queue, we have PCB of 7 and 2. They're ready to execute, and they have these associated pieces of hardware with them, and in PCB 3 would be in our ready queue as well, in a waiting queue, and then we would have a terminated queue, not necessarily a terminated queue, but a terminated process. So a queuing diagram represents queues, resources, and flows, right? So here we have our ready queue. It accesses the CPU. The CPU accesses I/O requests, time slice expires, creating a new child, etc. When a child is forked and a child executes, and an interrupt occurs, we wait for an interrupt, and when it occurs, we do the interrupt. After these are done, we go back to our ready queue. So, short-term schedulers or CPU schedulers select which process should be executed next and allocate CPU. Sometimes there's only one schedule in a system, and it's the CPU schedule. It's invoked frequently and in millisecond time slices, and it must be fast. A long-term schedule or job or process schedule selects which processes should be brought into the ready queue. Long-term schedule is invoked infrequently, seconds or minutes. It can be slower. The long-term scheduler controls the degree of multiprogramming. That is, the number of processes we can have running at the same time. Processes can be described as either I/O-bound processes, where they spend more time doing I/O than computations and has many short CPU bursts, or CPU-bound processes, which spends more time doing computations, few very long CPU bursts. A long-term schedule strives for a good mix of the two. We can also add a medium-term scheduler if the degree of multiprogram needs to decrease. It removes A medium-term schedule can be added if we need to decrease the amount of multi-programming degree, and it removes the process from memory, stores it on disk, and brings it back and forth from disk to continue execution swapping. So basically, we have a process beginning in the ready queue, goes to the CPU, something triggers, it gets swapped out, and partially executed process as a whole gets stored on the PC, swapped back in, and so forth. If the CPU hits up with an I/O waiting queue, it could then have an I/O operation and put us back in the ready queue. And this way, every time things switch, we will make better use of our CPU. In mobile systems, it can be a little different. Early versions of iOS only allowed one process to run at a time. Due to screen real estate, the user interface in iOS provides for a single foreground process controlled via user interface. This is not true in the newest versions, especially ones for like the iPads. It can have multiple background processes. And there are single short tasks, receiving notifications of events, etc. Android has fewer limits. Background processes use a service to perform tasks. Services can keep running even if the background process is suspended and it has no user interface. So, context switches. When a CPU switches to another process, the system must save the state of the old process and load the state of the new via a context switch. The context of a process is represented in the PCB. Content switch time is overhead. The system does no useful work. The more complex the OS and the PCB, the longer the context switch takes. And it can be time dependent on hardware support. Some hardware provides multiple sets of registers per CPU, and to make multiple contents be able to be loaded at once. So, when dealing with processes, we have to support the following operations: process creation, termination, and so on. Process creation, a parent process typically creates a child process, which in turn creates other processes, creating a tree. Generally, a process is identified and managed via a process identifier. Some resource sharing options could be parent and child share all resources, children share a subset of the parents, or they share no resources. Then there's the execution options. They could execute concurrently, or the parent could wait to continue its execution until the child terminates. Here is an example of a process tree in Linux. Init launches login, kthread, sshd, and so forth. So here's another example. In our address space, child will create a duplicate of the parent's address space, and the child has a program loaded into it. For an example, in Unix, you use fork. It creates a new process, which is literally a duplicate of the old one, including its variables. Can lead to some fun stuff. Exec is used after a fork to replace the memory with the program with a new program. So basically, we start at fork, parent calls wait, and while that's waiting, we execute, load in the new program, execute it, and exit, which then the parent can stop waiting and its flow can resume. So here's an example of a C program. We fork a process. If an error didn't occur, then if the ID is 0, it's a child process, and we do whatever we need to. Here we're going to execute an ls command. Otherwise, the parent will go forward, and we wait, and it will wait until the child process finishes. Okay. And in Windows, we use a slightly different approach. And by the way, in Windows, you no longer do this. You use much more advanced libraries that make it much more simple. You don't have to go through these hoops, but here's the basics underneath it all. You can have, you zero your memory in your startup info, and you set it to the start of the startup info block, and we create a child process, right? And we create a parent process that waits for a single process, waits for the child process to complete, and then it will clean up the parent process or finish up the parent process. Process executes the last statement and then asks the operating system to delete it using exit system call, usually. It returns status data from the parent to a child to a parent via wait, and the process's resources are deallocated by the OS. A parent may terminate the execution of a child process using the abort system. We might do this because the child has exceeded its resources. The task assigned to a child is no longer required. The parent is exiting and the operating system does not allow a child to continue if a parent terminates. Some parents, OSs don't allow a child to exist if a parent is terminated, and so if a process terminates, then all its children would also be terminated. Cascading termination. All children, grandparents, etc. are terminated, and it's initiated by the operating system. The parent process may wait for termination by using the wait system call. The call returns status information. So here we say PID wait for the status. If no parent is waiting, the process is a zombie, meaning it's just kind of ongoing and undead. And if the parent terminated without invoking wait, the process is an orphan, meaning its parent won't exist anymore, but it might. It's a bad situation. So, multiple processing architecture. Chrome is a good example. Some web browsers ran as single processes using threads. However, the problem is if one website caused problems, the entire browser would crash. Chrome is a multiprocess with 3 different types of processes. There's a browser process, which manages the UI, the renderer process, which renders pages with HTML and JavaScript, and a plugin process for each type of plugin. So now we'll move on and talk a little bit about interprocess communication. Processes within a system may be independent or cooperating. Cooperating processes can be affected by other processes, including sharing data. One of the reasons for using them is obviously sharing information, speeding up computation, modularity, or convenience. Cooperating processes need some sort of interprocess communication, or IPC. There are 2 major models: shared memory and message passing. Okay, so we've got process A, which is message passing, and process B. And process B would write into a queue that process A would write into a queue that process B would read from, and so forth. In shared memory, we actually just make a piece of memory available to both A and B. Now, in terms of security, message passing is typically more secure. So, cooperating processes. Independent processes cannot affect or be affected by the execution of another process. Cooperating processes can affect or be affected by the execution of another. Process cooperation gives the advantages we talked about before. So, one of the ways to think about this is in terms of a producer-consumer problem. It's a paradigm for cooperating processes. The producer process produces information that is consumed by a consumer. There's 2 approaches. The unbounded buffer places no limit on the size of the buffer, other than memory, obviously, and a bounded buffer assumes there's a fixed buffer size. So we're going to look at a bounded buffer solution with shared memory. So here we've got our shared data and our item buffer, our buffer of data, and our in and out position. Now, the thing about this is it can only use buffer -1 elements. And we share this data, but we are limited. We then would produce an item in a process. It's while true, produce an item in next produced, and while we're full, we're going to do nothing until we're no longer full. Now remember, the converse is we reduce it working in another process, so it will free up this buffer, and it works because we have shared memory. So here we get stuck waiting for an opening, and now we produce the item, and we update our buffer size. In the consumer, we say while true, while the number of input and outputs are the same, we do nothing until we can actually consume something, so there's something there. We grab the item, and we modify our buffer size again, and continue through. And again, to note that because these are separate processes, but they share memory, they can affect each other. Now there's dangers of collisions and that sort of thing, but we'll talk about those later. So shared memory has an area of memory amongst the processes. The communication is under control of the processes, not the OS. And we need to provide a mechanism that allows users, processes, to synchronize their actions when they share access, because otherwise you can stomp on things and accidentally overwrite them. So the way to think about that is, say process 1 grabs a value from memory. Okay, say it's a 5. And process 2 comes along, and process 1 is going to do some computations. Process 2 comes along and it takes that same value of memory and changes it to 3. Process context switch happens and it goes back to the first process, but it's expecting a 5, so its computation will be wrong. The other approach is to use IPC, message passing. And the way that works is there's a message system that processes communicate with without resorting to shared variables. Typically, they'll have 2 operations, send and receive. The message size can be fixed or variable, and if process P and Q wish to communicate, they need to establish a link, and they exchange messages via send and receive. So here are some questions. How are the links established? Can a link be associated with more than 2 processes? How many links can there be between every pair of communicating processes? What's the capacity of a link? Is the size of a message that the link can accommodate fixed or variable? And is a link unidirectional or bidirectional? So let's look. Implementation of a communication link can be done physical via shared memory, and we're right back there, a hardware bus, or a network. Logical, that's the physical approach. Logically, we can have direct or indirect, synchronous or asynchronous, automatic or explicit buffering. So direct communications. Processes must name each other explicitly. Send, P comma message, sends a message to process P. Receive, receives a message from process Q. Links are established automatically. A link is associated with exactly one pair of communication processes. Between each pair, there exists exactly one link. The link may be unidirectional, but is often bidirectional. There's also an approach called indirect. Messages are directed and received from mailboxes, also referred to as ports. They're kind of like queues. Each mailbox has a unique ID. Processes can communicate only if they share a mailbox. Some of the properties are the link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communications links, and the links may be unidirectional or bidirectional. This has interesting implications because you can do broadcasts. So some of the operations: create a new mailbox, send and receive messages, destroy a mailbox. Primitives are similar. You send a message to mailbox A, receive a message from mailbox A. So how do we share? For example, P1, P2, and P3, which are processes, share mailbox A. P1 sends, P2 and P3 receive. Who gets the message? Well, if you allow a link to be associated with the most 2 processes, there's not a problem there. Or you allow only one process at a time to execute, or let the system arbitrarily have the receiver pick. The sender is notified who the receiver was. I think this is kind of a hinky solution. So message passing can either be blocking or non-blocking. Blocking is considered synchronous. A blocking send, the sender is blocked until the message is received. A blocking receive, the receiver is blocked until a message is available. Non-blocking is asynchronous. The sender sends a message and continues on its way. The receiver receives a valid message or no message, and continues on its way. The different combinations are possible. If both send and receive are blocking, it's called a rendezvous. So, using synchronization and messaging, the producer-consumer becomes rather trivial. While true, produce the next item produced, and then we send it, and it'll wait till we get our response. And on the other side, we we go in an infinite loop until we receive, and once we receive it, because it's synchronous, the other guy's free to move on, and we can go in and do it all again. So, buffering is often important when dealing with processes. Queue of messages are attached to the link, and it can be implemented in one of three ways. Zero capacity. No messages are queued. The sender must wait for the receiver at rendezvous. There's a bounded capacity, finite number of messages. Sender must wait if the link is full. And an unbounded capacity. Infinite length, and the sender never waits. Of course, that's not truly infinite. So, some examples of IPC systems. POSIX is a good example. The process first creates shared memory segment. Also used to open an existing segment to share it. And if the process could write to the shared memory, it'll give you success. So here's the POSIX producer consumer, right? We open our shared memory and configure this forward, and we write to the shared memory, and that is our producer side of it. And the consumer maps the shared memory into its object, and it tries to read from it. Since these are synchronous, you'll stick around till they're both done. So in Mach, it's message-based, so even system calls are messages. Each task gets two mailboxes, kernel and notify. Only 3 systems calls are needed for message transfer: message send, message receive, and message RPC, which is like a remote procedure call, or a remote method call, however you want to think of it. Mailboxes needed for communication are created via port allocate. Send and receive are flexible, for example, 4 options: wait indefinitely, wait at most n milliseconds, return immediately, and temporarily cache. Message passing centric via advanced local procedure call facility is how it can be done in Windows. And Windows is very message passing centric. The whole OS runs on that concept. It uses ports like mailboxes to establish and maintain communications, and the communication works as follows. The client opens a handle to the subsystem's connection port. The client sends a connection request. The server creates 2 private ports, communication reports, and return the handle of one to the client. The client and server use the corresponding port handle to send messages or callbacks to listen for replies. Callbacks are what a message is in Windows. Often it is essentially using a pointer to a function. So in Windows, we get a connection request, and we get a connection port and a handle to our server. We also get our client communication port and a server which talks to a server communication port, and they talk to each client and server. And then there's a shared section object, which is less than 256 bytes. Okay. So communications in client-server systems are handled by a couple different methods. Sockets, RPC or remote procedure call, pipes, or remote method invocation. A socket is an endpoint for communication. We have an IP address and a port, a number. So you might see a port like, Microsoft.com, which is DNS actually, :80, which is the HTTP port. So here, 161.25.19.18:162.5 refers to port 16.25 on that IP. Communications happen between a pair of sockets. All ports below 1024 are well known, such as HTTP, HTTPS, FTP, and so forth. There is a special address, 127.0.0.1, which is called the loopback address or local host, and that is the system the current process is running on. So socket communication, we have a pair. In Java, there are 3 types of sockets. And in general, for TCP/IP, there is connection-oriented, which is like a phone call. Connectionless, which is like a telegram, an email. and multicast sockets, and it allows one-to-many type communications. So here's a date server. Okay, so we create a new socket. Now we listen for connections in an infinite loop because we want to keep this service running. And this blocks, when it receive it, we get the output stream. We write the date back to the input stream, and then when we're done, we close the socket and resume listening for new connections. So the server's always listening, but the connections come and go. Remote procedure calls abstract the idea of a procedure call between processes on network systems, and it uses different ports for service information. They have the idea of stubs on the client proxy for the actual procedure on the server. The idea here, and you do this all the time these days, but it goes under various different names: REST, web graph, I think that's what it's called, from Facebook. I can't remember the name. So basically, on the client side, we have a proxy. The client-side stub locates the server and marshals or packages the parameters. The server-side stub receives this message and unpacks the parameters and performs a procedure call and then sends the results back. On Windows, stub code is compiled from something called Mitle. Mitle is no longer used, though. They actually just use our REST for it. The data representation is handled via external data representation, and to deal with like big endian and little endian type problems. Now, that is also no longer used because they tend to use JSON, JavaScript object notation, as the method for sending, where you don't have to worry so much about it. Remote communication has more failure scenarios. So we have to ensure that messages can be delivered exactly once rather than at most once. OS typically provides a rendezvous or matchmaker service to collect the client and server. So here's the execution. User calls kernel to send an RPC message. Kernel sends message to matchmaker to get a port. Matchmaker receives messages, looks up an answer. Matchmaker replies to the client with its port. Kernel places P in the message. It sends the message. The daemon listening to the port receives it, processes it, and sends the result back. Okay. Another option you see often in Linux and sometimes on Windows is pipes. It acts as a conduit between two processes. Is the communication we have to consider unidirectional or bidirectional? Is it half or full duplex, meaning can they transmit at the same time? Must there be a relationship between the processes? And can they be used over a network? Order-neat pipes can't be accessed outside the process that created it. Typically, a parent process creates a pipe and uses it to communicate with a child process. Named pipes can be accessed without that relationship. So ordinary pipes allow communication in standard producer-consumer style. The producer writes to one end, the write end. Consumer reads from the other end, the read end. And they are unidirectional. They require parent-child relationships between communicating processes. Windows calls these anonymous pipes, and there are samples in the textbook. Then there's also the concept of named pipes. They're more powerful than ordinary pipes. They are bidirectional with no need for a parent-child relationship, and several processes can use the pipes for communication. Both Windows and Unix have them. So we've discussed the basics of processes. They're very important, and they have a good deal of complications, so I would suggest reviewing this carefully.